Okay, hello again. Take 3. Yeah, third time's the charm, they say. Okay, sorry. Medyo fail itong week. Pero, let's just push. Uh, medyo okay naman, there's just some interruptions. Let's just push. Hopefully you guys are still learning anyway. Kahit may konting problems. Alright. Malapit naman na. We're almost there. So, I was saying, well, if we want to convert the idea into code, we need to think about what variables do we need to keep track of. Okay, so what do we need to keep track of? We need to know our current position. We need to know how many swaps do we have left. And we need to know, are we in the top row or in the bottom row? Right? And then we're going to start with 0 in the position, k swaps, and we're at the top row. Okay, it's possible we also start at the bottom row, okay, but we can think about that later. Let's say we start at the top row for now. What's going to happen if I start from the top row? Well, I can either take one step, and then that means I'm going to end up at position 1 in the bottom row, and I have k minus 1 swaps left. Or I can take 2 steps on the top row. That means I end up at position 2 in the bottom row with also k minus 1 swaps left. Or position 3 in the bottom row, tapos k minus 1 swaps left. And in each case, my answer increases by a certain amount, right? Here, since I walked once, I increased my answer by top 0. Here, it increases by top 0 plus top 1, and so on, right? And there are more steps there, but I'm not showing them because there's no space. But you can keep going, right? And then what happens down here? If I'm at position 1 and I have k minus 1 swaps left, I'm at the bottom row, I can take one step forward and I'm going to be at position 2 in the top row now. And then I have k minus 2 swaps left, and my answer will increase by bot 1. Or I can take 2 steps, so my answer will increase by bot 1 plus bot 2. And I will end up at position 3 on the top row. Tapos, k minus 2 steps, k minus 2 swaps left, and so on. Right? Do you see it? Okay, so Walsh Letran. Okay, sige. Has a question, but he says never mind. So let's continue. Okay, so how do we write this in code? Well, if you look at one path of this tree, of this diagram, if you look at one path, this is exactly like, let's say you magically know how many steps to take at every step. How many steps to take at every swap. then it's some kind of path to this through this tree, right? Some kind of path through this tree. Try saying that 10 times fast. Okay. How would you write the code in that case? Well, it's going to look like this, right? For swaps in range k up to 0, and then you go down one. So for those who are not familiar with Python, this is just looping from k to 0. Okay, so k minus 1, k minus 2, downwards, right, to 0. And then I initially at position 0, and my answer is 0. And let's say I'm at the top row. Okay. If I had a magic function that says know how many steps exactly to take at this iteration, magic pause and stop. And then what do I do? Pause is equal to new pause. Answer is equal to something. Okay, I'm not going to fill in the details. It's sum from pause to new pause. And then top is now, I flip it. If I'm top before, then I'm not top now. If I'm bottom before, if I'm not top before, not top will mean true. So that's switching a boolean. Okay, this is how I might code it if I knew this magic position. But the thing is, we don't know that magic position. That's why we're trying all possible positions. Pero how do we write it? Well, etong for loop na to, you can think of a for loop as a poorer version of recursion. Kasi what does a for loop do? If you're at iteration k, you can only move to one new state at every step. So I go to k minus 1, but I have exactly one position and answer and top only. And if I go to k minus 2, I have only one position, answer and top. And if I go to k minus 3, I also have only exactly one position and stop. Okay, ano yung drawing natin kanina? I want to account for the possibility that if I move from k to k minus 1, I want to try to explore many different options. Okay? So I want to write this in a different way. Okay? How do I write this in a different way? I'm going to try to convince you that this is a different way of writing a for loop. Okay, I'm gonna try to convince you that, okay, and we have to have the answer somewhere. So sum boss of the new boss something plus. Okay, I'm gonna try to convince you that this is doing the same thing as the loop that I wrote previously. This one. Why? Well, assuming I gave it the right starting variables, right? So I'm gonna call best 0 k, and then let's say true. And then if I print that, that's the same as this, and then print ans. Do you see why? Okay, what does the for loop do? I currently have a position, number of swaps, and then top, and then answer. And then what do? I update position to new position. I update position to new position. The number of swaps that I have goes down by -1 at the end of this loop. Here, I reassign swaps to swaps -1. My top becomes not top. Top becomes not top. And then I do something here. The answer increases by this guy. The answer increases by this guy. Okay? Are you convinced? This is the same thing. This is doing the same computation as the loop, except that I wrote it as a recursive function. Okay? So if you try to imagine what's going to happen, if I start from 0k true, this is going to move from 0k true to best new pos k-1 false. And then from there, this will call new pos, a different new pos, k-2 true, right? And that's exactly what's happening if you just loop, right? You're getting a new position at every time. You're decreasing the swaps by 1 at every time, and then you're swapping from true to false. And that's also what's happening here. Okay. Why do I want to write it like this? Kung yung for loop, you're limited to doing one path. Okay, this is the point of writing this function recursively. The point is, I can do this. I can call multiple recursive functions. I can call multiple sub function calls here. I can say 0, not 0. I can say best 1 swaps -1, not top. And then I can also call best 2 swaps -1, not top. Best 3 swaps -1, not top. And then if I try to get the maximum of all of them, what's going to happen? That's effectively doing this tree thing here, where I try all the choices and then get the best option out of them. Right? So you can think of this recursive function as a generalization of the for loop. if you have a recursive function that calls itself once, it's kind of like a for loop. You're going from swaps to swaps minus 1 to swaps minus 2. Okay? But you have no choice. You kind of need this magic function kasi you can only go to one position at every step. You need to have this magic function. But if I want to try all possibilities, then this is the way to do it, to get rid of the magic function, right? Okay, and then this will just branch and so on. Okay, hopefully the picture is clear. So now let's actually code it. So here's what I'm going to do. I'm going to define a function. Let's call it best. It's the best way to get the path, assuming I start at position pos. And then the number of swaps I have left is swaps. And then another variable saying, am I at the top or not? What do I want to do here? Let's say initially the answer is 0. Then I'm going to try all the ways to walk a number of steps. So for the number of steps in range, let's say 1, 2, well, if I'm at position pos, okay, let's just do this. Instead of saying steps, let's just say new pos. That's easier to think about. My new position can be from pos plus 1 up to n, right? And what do? I try to make a path from that new position one less swap, and now I switch rows. And then my answer increases by let me write it this way. Okay. Hopefully this is clear. If you haven't seen this before, this is just notation that says take the list from this index up to this index exclusive. And that's what I want, right? And I want the sum of everyone. Okay, let me do this. Top row, if top, else bottom row. Hopefully that's clear. Top is a boolean, yes. So if it says true, then I'm gonna take the top row. If it says false, I'm gonna take the bottom row and get the sum from here to here. And then I want the maximum out of all the options, so I'm gonna do that. And then down here, I'm gonna return the answer. Okay, so that's the basic structure of the code. Okay, of course I can optimize this. You can use what you did in problem C to make this faster so that you don't have to compute this sum over and over. But that's the idea. Okay, so I'm not gonna show how to make this part faster because you can apply what you did in problem K. Okay, and then what? Well, actually, that's it. If pos happens to be at the end already, then uh, this won't do anything because pos plus 1 is going to be bigger than n minus 1, and this won't do anything. You just return 0. But we also have to add some extra checks. We can actually only do this if we still have at least one swap. So if swaps greater than 0. Okay, otherwise, well, the default is just don't take any swaps, right? So if you don't take any swaps, it's going to be uh, this one, except I go all the way up to the end. Okay, is that clear? And then let me read the input as before. Okay, let me do that here. Now what do I want? My final answer is going to be, going back to this picture, this one. Well, I have two possible starting points. I can either start here at the top row or at the bottom row. So how do I do that? In code, that's going to be max best 0. I have k swaps and I am at the top, or 0 still, k swaps, but I'm at the bottom. Okay, hopefully this actually works. Let's try. Let me get my sample input. Okay, that's not what I want. And yeah, it seems to work. And actually, I believe this is correct. The only problem is what? Well, this is slow as hell. Okay, so Walsh says this will do. Yeah, that's right. You can shorten it. But anyway, for those who are not familiar, let's just keep it in. Okay, so this is correct, but it's slow as hell. Why is it slow as hell? Well, let's look at this picture again. what's going to happen here? You're going to have a tree of k levels, and then at every level, what's going to happen? You have roughly n branches. So this is going to be slow as hell. Why? N branches, and then n, 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 and then n, 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 and this is going to explode. Okay? How many things, how many recursive calls do you have to do? Approximately, roughly speaking, well, at every step, you're multiplying the number of branches by n, right? Branches multiply by n at every level, and you have k levels. Okay, so this is actually something like n to the k. The amount of work you need to do is n to the k. That's hopeless. Because what's n in this problem? N is 1000. What's k? K is also, worst case, around 1000. Man, this is an unimaginably large number. The universe has ended. Your program is still running. If somehow your computer survived, your program is still running. The answer is not there yet. Even 1000 to the 10 is already very, very large. That's 30 zeros. Definitely not gonna work. This is 1 followed by 3000 zeros. That's too much. So, yeah, Walsh suggests we can memoize this. What's memoize? Okay, what do we do? Well, the thing is, so remember, what are we going to try to do to make things faster? Don't repeat computations that we've done before. Let's explore what happens if I have 0. Let's take a concrete number. Let's say 10 true. What's going to happen? Oh, before that, there's actually one improvement we can do. So remember, our choices were, you take 1, and then you swap, and then you go to the bottom. Or you take 2, then you swap, and then you go to the bottom. Or you take 3, you swap, go to the bottom. But you can also reach this in a different way. You can say, at position 1, I'm not going to use up my swap. I'm just going to move to position 1. So I'm at position 0. I'm just going to move to position 1 without using up my swap. Why? Because this case is covered down here. If after position 1, I want to swap, then I just swap to position 2. And use up one swap. Okay, this case is also covered if I do this. This case will be, first, I stay at position 2 without using up a swap. So I stay at position 2 and then swap to position 3. Swap at position 3. Okay, why did I do this? Why is this better? Well, we can simplify the logic a little bit. Because this time, instead of having n choices, we just have 2 choices now. Either we actually swap and use up a swap, go to the next position, or we just stay at the row where we are and don't use up our swap. Okay, so take a moment to think about it. Are you convinced that this will also try all possible paths? If I just limit myself to these 2 choices. Stay in the same row and don't use up a swap, or swap right now and use up 1 swap. Right? It's the same, right? It's going to try all paths still. Right? So the first one will be do not swap at all, and then like that. Right? Hopefully you're convinced. If I do this, if I limit myself to two choices at once, it's the same thing. So let me simplify my code first to make it a bit easier. Okay, so what's going to happen here? I now have only 2 choices now. It's either I don't swap, which means I go to pos plus 1, don't decrease the number of swaps, and I stay at the same row. And my answer increases by... Let me think about the answer later. Let me think about the choices first. My other choice is I still go to pos plus 1. I now decrease the number of swaps, and I move to a different row. Okay, and then at this step, I increased my answer by something pos. And that something depends on, am I in the top row right now or in the bottom row? Okay, and then I have to be a bit careful here now, because unlike here, I won't automatically end if I'm at the last position. I have to actually write a base case. If my position is now n, then I can't do anything anymore. I'm done. Otherwise, I do this. And also, I can only do this second move if I have swaps left, right? This is the same check I did before. So I'm going to do this only if I have enough swaps. Otherwise, let's just say 0, because that's options invalid. Okay, a lot cleaner. And let's check that it actually still works. Okay, it still works. Okay, let's try to analyze. Does this make my solution faster? Well, it should, because what happened? Earlier, what's happening? At every step, earlier what's happening is at every step, I'm making n branches. But this time, I only have 2 branches. So it should be a bit faster. How much faster is it? Okay, if I'm branching by 2 at every step, and I have n steps, that means I'm at big O of what? Okay, this one should be, if you're thinking 2 to the n, that's right. Okay, so 2 to the n is at least slightly better than, or 2 to the k, because I have k levels, right? 2 to the k is slightly better than n to the k, but it's still really slow as hell because k is 1000 still. 2 to the 1000 is still a really, really large number. So this is not gonna finish before the universe ends. Okay, but there's actually a simple trick you can do to make this faster. Let's take a look at what's happening exactly. If I start with 0, 10, true, what happens? I go to 1, 10, true, and 1, 9, false. Then down here, what do? I go to 1, 2, 10, true, 2, 9, false. Down here, 2, 9, 2, 8, true, 3, 10, true, 3, 9, false, 3, 9, 3, 8, true, 3, 9, false, 3, 8, true, 3, 8, true, 3, 7, false. I'm just running the recursion manually. What do you notice? There's a 39F here. There's a 39F here. Another one. Actually, this whole thing is going to be the same as this. And the answer down here that I'm going to get from this recursive call is going to be exactly that I get from this recursive call. What do we want to do to make it faster? Let's not repeat computations we've already done. So, how do I do that? The first time I see 29F, I'm going to store the answer somewhere. And then the next time I see 29F, instead of proceeding with the recursive call, um, what do I do? I already know the answer to 29F. I'm not going to be stupid and repeat the computation. I'm just going to get the answer that I saved before. Okay, how do I do that? How do I implement that idea? So let's go back to the code. So here's what I'm going to do. Let me say saved answer. And I'm going to use a dictionary for this. If you haven't seen this before, I kind of introduced this in round 1. I think it was introduced again in some other round as well. A dictionary just allows you to map some key to some value. Okay, it's kind of like the Chad version of a list, except that instead of just number indices, you can index by whatever you want. Okay, how am I going to use that? I'm going to say if pos swaps top is not in saved answer, then that's the only time. It means I'm seeing pos swap stop. This exact combination of pos swap stop, I'm seeing it for the first time. So I'm actually going to compute it. But instead of returning it immediately, let me save the answer. Okay, down here, and then down here, I return the saved answer. So what's the effect of this code? The first time you see pos swap stop, it's not going to be in saved answer. So this thing is going to run. And it will call it recursively. The second time you see this pos swap stop, what's going to happen? It will already be in saved answer, so this will be skipped, and then you just return the saved answer. And that's exactly what we want to do. And why does that make everything much faster? Well, the idea is, when you see this branch again, you're not going to do this entire computation anymore. Okay? This branch, this 39F, you're not going to do anymore because you already saw the 39F here. So if you imagine what's going to happen is the tree without that trick that I did, without saving the answers, it's just going to look like this. But if I save the answers, okay, what's actually going to happen is your recursion tree is going to be much thinner. So this doesn't even exist because I didn't call these guys in the first place. It's going to be like this. Right? So what's going to happen at this step? this step is not going to take 2 to the k anymore because these guys have already been saved before, and you're just going to pick up the answers from the dictionary, and that's going to be pretty fast. So actually, the work here is something like O of 1, a small constant number of operations. And if you try to imagine it, this whole thing is going to look like this. You have a branch here that's n, and then you have a few stuff sticking out, but that's still also around n. Or actually, sorry, k. Um, well, it's a bit more complicated than that, but I'm running out of time, so I'm not going to explain everything in detail. But the idea is you do this simple trick, don't compute all the answers, and the amount of work that you're doing will magically vanish into something small. Okay? It's not gonna be O of k. So more precisely, it's gonna end up being O of nk. Uh, so it's getting late, so I'm not gonna explain all the technical details right now. What I would encourage you to do first, if you've reached this far and you're not totally confused already, it means you're ready for this idea. But if you're still confused, then it's fine. You can practice with problem K first and some easier problems. This is actually one of the harder problems that we've given out, um, because the technique is somewhat advanced. Well, not really if you're used to it, but for a beginner, it's somewhat advanced. Um, so try it first, and then we can talk about the details of why exactly it's nk in the Discord server. Okay, and also, the code as is that I showed here, I think it's not going to work. It's going to be slightly too slow, and you have to do a few tricks to make the running time even lower. And you have to get around some stuff in Python that's Python specific, like the fact that there's a recursion limit in Python. Okay, but that's all details. The thing I want to show in this stream is the main idea, which is if you have something that's exponential and you have in these exponential branches, you have recursive calls that are overlapping with each other. And you know that the answer to one will exactly be the same the second time you call the same function. Then you don't have to repeat the computations you've done before. Just store the answer that you already have computed before and retrieve that same answer when you encounter the same parameters in the function. Okay? And this is something that people call dynamic programming. So if you want to learn more about this is the term you want to Google. Although, yeah, there's no meaning. This word doesn't mean anything. The person who invented this technique just wanted something that sounds cool, and so that's what we call it. But anyway, that's the idea. Alright, so it's getting late. I better end the stream now because it's too long. But I encourage you to try this on your own. and we can talk more about how to analyze this properly and some other things that you need to do, details that you need to get this problem right. So don't hesitate to ask for help in the Discord server if you've reached this far and this is your first time to see this technique. This is a good opportunity to practice with this problem. And we're always in the Discord server to help if you have questions. All right, so I guess I'll end the stream here. So again, if you guys have questions, just ask in the Discord server. Yeah, this is pretty confusing the first time you encounter it. If you're not very familiar with recursion, kung hindi ka sanay, it's kind of hard to grasp, but you see it a few times and then you will just, by practicing more, you will kind of get it. Okay, I can't really explain um, how. You just kind of have to practice it and then it will come naturally at some point. Okay, uh, yeah, that's really how it is. But don't worry, we will help you in the Discord server. This is something that you can't rush in an hour or so. You just need to take some time to think about it and maybe spend some time asking questions, getting help. So that's it for now. Uh, yeah, sorry for the technical disruptions, and I hope you guys learned a lot of things today. I hope you guys enjoyed the problem set. Yeah, Walsh says recursion breaks my soul. Don't worry. Uh, you will break recursion's soul after you've mastered it. But you just need to practice it. Okay. So yeah, that's all for now. If you need help, we're always in the Discord server. And that's it. See you guys next week. All right. Bye.